This is a little short video on the natural exponential function, and I know I introduced it a little bit in class, but I wanted you to see where it came from and the history behind it. So we're talking about the natural exponential, and the word that I want you to remember when I talk about this is if you hear the word continuous. If you hear the word continuous growth or decay, we're going to use the natural exponential function. The other thing is you use the natural exponential function a lot with half-life and doubling time. So a lot of times it's understood that you're using the natural exponential function when you hear about half-life and doubling time along with growth and decay. There is an exponential base that is important to the natural world. The constant is sometimes referred to as Napier's constant after Scottish mathematician John Napier, who was credited with introducing logarithms. Sorry, I can't talk today. But we'll talk more about that later. This base is referred to as E. So E is a number. Okay, E is a number. It's a constant approximately equal to 2.71828146. It's like pi, but it keeps going and going and going. It's irrational. You might wonder why E is the letter we use. This is actually to honor another mathematician by the name of Leonhard Euler. That's the German pronunciation. Click on his name to learn more about this impressive mathematician. Well, I don't have a link here, but if you Google it, he's done quite a bit. Well, let's get back to the natural exponential function. Since base E is 2.71, if we were to graph y equals 2 to the x and then y equals 3 to the x, do you see how 2.71 is close to 3? So the exponential function y equals e to the x is very close to y equals 3 to the x. Okay? Now let's look at the formula we're going to be using for continuous. It's y equals a e to the kt. All right, there's your base E. So E is a number, all right, it's continuous, and it's going to be, if I use the word continuous, just to refresh your memory. A is still your initial value. K is now either your growth or decay, but it's different in this one. If K is positive, that's the K I'm trying to write, guys, is positive, it's growth. If K is negative, it's decay. All right, so you don't have to worry about the 1 plus R or 1 minus R. So let's put a big warning on here. Warning, when you have a continuous function, when you have base E, 1 plus R or 1 minus R, do not use. Okay? Only with this. You're going to use it for other things, but not with this. Okay, the natural exponential function, growth and decay. It's a growth function with a continuous rate of k. This is a decay function with a decay rate of k. So they put the negative and positive here for you. They use p sub 0, which is the same thing as we've been using for a. And before, when we use y equals ab to the x, when you had to have your b was 1 plus r, 1 minus, notice we had 1 minus r. Notice we have x here. You could really write this as ab to the t, because most of the time, x is time. Most everything depends on time. So when we talk about this base E, it's a continuous growth rate. Note, this continuous formula when the growth is known to be continuous. Our textbook will clearly state when a situation requires continuous. I will tell you. I'll make sure. So for example, if a population starts at 1,000 and is growing at a continuous rate of 3% per year, write the function. If you'll notice, I have y equals ab, excuse me, I erased that, y equals ae to the kt. You'll notice if it's continuous, all you do is change this to a decimal and put it in the k spot. And since it's growing, it's positive. So it's going to be y equals, starts at 1,000, e to the 0.03t. Asymptotes. Now this is important. We're just touching on this a little bit so you'll see. But a function f of x has, well, we will spend some time talking about them. A horizontal asymptote is y equals L, a limit, if the function approaches that limit as x approaches positive and negative infinity. This means that we are looking to find out what value of y the function approaches when we are very large or positive or negative values for x. The exponential y equals ab to the x has y equals 0 as a horizontal asymptote. And we've looked at that. If you look at any kind of function you have here, so let's look at y equals, if we did a growth function, do you see that here's my x and here's my y? You will see that it is approaching 0 eventually, but never touches it. If it was a decaying function, you could have that going on. Again, it's approaching 0, it's just approaching it from a different direction. And then it says find the horizontal asymptote of y equals 8, 0.7 to the x. So if we were to graph this, this is kind of interesting. This crosses at 8 because 8 is my initial value. So the function, and it's decaying, so it's kind of going like this. So here's my x here, here's my y here. It says find the vertical asymptote. Well, it's approaching the x-axis again, so it's a y equals 0. And so you can say x-axis, or you can say y equals 0. We will do more with the limit notation later because that's what this leads into. But that's just, this is just an introduction. Notice we eventually, the y value looks to be 0, but it's not really true. And the horizontal asymptote is a horizontal line, so its equation must be written in the form of y equals. And the horizontal asymptote is y equals 0. Have a good weekend, guys.
Book club voting sheet.